Hi, my name is Nicholas Varghese, and today I'll be presenting my Physics 21-22 Lab 5 on Faraday's Law. To begin, the purpose of this lab was to explore Faraday's Law and observe the interaction between a falling magnet and a tube of aluminum foil. We used a magnet and aluminum foil to create this scenario in order to observe magnetic fields and flux in real life. In addition, we also wanted to create a computational model to simulate a bar magnet being dropped through a conductive tube such as aluminum foil to simulate what we are observing in real life. Before we begin this lab, it'll be important to understand some basic physics principles. The first big physics principle that's involved is Biot-Savart law as it applies to the magnetic field of a bar magnet. It will also be important to know Faraday's law in order to find the current in each small ring of our aluminum foil, and we will be also using the formula for gravitational force and magnetic flux, which will be discussed in my model in the future. In addition, we will also be using Newton's second law in our model to update the position and velocity of the magnet, as well as Newton's third law to find the force on the falling magnet by the tubed rings. For this experiment, we are taking a magnet and aluminum foil and recording how long it takes for the bar magnet to drop through the aluminum foil tube. I started by using my magnometer app to find the north pole of the magnet, and then dropped my magnet through the foil and recorded the observation 5 separate times to find an average. To the right, you can see each individual trial as well as the resulting average at the bottom of 1.16 seconds. So what happens to the magnet during these trials? The magnet falls vertically through the tube. It actually fell slower than I had anticipated and experienced some resistance along the way. So how does the magnet falling through the tube compare to free space? I found it took longer to fall through the foil than in free space, and this could possibly be explained by magnetic braking. The next part of this lab was to create a computational model for my experiment. The first thing I did was add the initial conditions of my aluminum foil, which were the width, length, and radius, as you can see above. From there, I added the mass of my magnet, the magnitude of magnetic dipole moment, as well as a function to calculate the magnetic field of the bar magnet, which can be seen in the blue box. Then, using this magnetic field function, I created a function to find the magnetic flux, which can be seen in the red box. This is helpful because I wanted to know the flux along each ring due to the falling magnet. From then, I will also use Faraday's law to calculate the current induced in each ring by the falling magnet, and then the Biot-Savart law to calculate the force exerted on each current carrying ring by the falling magnet. From here, I was then able to use Newton's third law to calculate the force exerted on the falling magnet, and then calculate the net force to update the magnet's velocity and position, which relates to Newton's second law. This is the graph that was outputted from my computational model. The middle section is where the velocity is constant and there is no net force. This is the period of time when the magnet is falling through the tube. During this, it has a gravitational magnetic force acting on it. In the model, we got the time in the tube to be 1.5 seconds, which is much longer than the real time of 1.16. So now let's interpret the simulational model. The color on the tube indicates the current flowing in the ring. Red indicates counterclockwise and blue clockwise rotation according to Lorentz law. If we flip the magnet, nothing would happen, but the current would flip and flow in opposite directions to what we see now. The total time in the system, in the real world, ended up being less than the model in the computational. However, to make the model more accurate, we could just simply split the tube into more rings and take into account air resistance. The shape of the velocity versus time plot also tells us that the force acting on the bar magnet steadies and eventually becomes zero. So now we will answer some what-if questions. What if the resistivity was reduced to zero? Well, then the induced current and magnetic force would increase and oppose the change in flux. This would make the magnet fall much slower and take longer to fall. If the tube had holes, then the current would weaken, which would weaken the magnetic field. Since the magnetic force from the tube would decrease, the magnet would fall more quickly because there is less resistance.